Alright, now finally, let's talk about how to find solutions to these systems of differential equations we've been talking about. The easiest case is when we have a homogeneous system, x prime equals ax. The matrix A is all constants, no functions of t in there. And it's non-defective, meaning if it's n by n, we can find n linearly independent eigenvectors. And if those eigenvalues are all real, that also makes this the easiest case. So let's look at this case first. So let's fix this matrix A, which is n by n, with real entries. Now usually solving x prime equals ax is as easy as finding eigenvalues and eigenvectors of A. So in particular, we have the theorem if V is an eigenvector of A, with real eigenvalue lambda, then x equals e to the lambda t times the eigenvector is a solution of x prime equals ax. So this is sort of easy to see if we just plug and chug. So we have x prime, the derivative is going to be, v is a constant vector, so all we have to do is look at this function really, lambda e to the lambda t times this vector. And a e to the lambda t v is, now e to the lambda t is just a scalar, so we'll take that out, e to the lambda t av, but av, v is an eigenvector, so that means av is a multiple of v. We said the eigenvalue is lambda, so this gives us e to the lambda t lambda v, and we can see that these are just the same things. Lambda is a scalar, so we can pull it out. So that's how we can get one solution for every eigenvalue and eigenvector. And furthermore, we have the following. So suppose we find all the eigenvalues and linearly independent eigenvectors for all the eigenvalues. So if, let's say, v bar 1 through v bar n are linearly independent eigenvectors, of A with eigenvalues lambda 1 through lambda n, and it's okay if the eigenvalues are repeated, so if two different linearly independent eigenvectors have the same eigenvalue. All right, possibly with repetition. Then e to the lambda 1 t v1, so exponential of the first eigenvalue t times the first eigenvector, etc. So we do that. I'll write out one more. e to the lambda 2t v2, etc., up to e to the lambda nt vn are linearly independent solutions. And then the whole solution set is C1 e to the lambda 1t, first eigenvector, sum of that. So basically this is a fundamental set. So all linear combinations of these form the general solution, the set of all solutions. Cn e to the lambda nt nth eigenvector. So we know that the solution space of x prime equals ax, if we have an n by n matrix, is n-dimensional. So if we find n linearly independent solutions, then we know that they form a basis. So let's just look at the Wronskian. The Wronskian of e to the lambda 1t, first eigenvector, etc., up to e to the lambda nt nth eigenvector is the determinant of the matrix where the columns are e to the lambda 1t, first eigenvector, e to the lambda 2t, second eigenvector, etc., e to the lambda nt nth eigenvector, now if we have an entire column multiplied by a constant, we can take that out of the determinant. So for every single column here, we can take out the exponential part. So that's e to the lambda 1t, e to the lambda 2t, etc., e to the lambda nt, determinant of just the eigenvector matrix. And we said these were linearly independent eigenvectors. So that means if we take the determinant of this matrix, it's not going to be 0. And if we look at these exponentials out in front, well, exponential functions, no matter what we plug in for t, are not 0. So the Wronskian is not 0, and that means that these columns, these function columns, are linearly independent functions, vector-valued functions. So e to the lambda 1t v1, etc., up to e to the lambda n t vn are linearly independent as vector-valued functions. All right, so now that we know how to find some solutions, let's do an example. Let's solve x prime equals ax, where A is the matrix -1, -1, 1, 0, -3, 2, 0, -5, 4. So first thing we have to do is find the eigenvalues, and we'll use those to find the eigenvectors. And then we pretty much just plug in the eigenvalues in the exponentials and put them next to the eigenvectors, and those are the solutions. So first, let's find the eigenvalues. We'll find the eigenvalues by solving determinant of a minus lambda I equals 0. So we have determinant of -1 minus lambda here, -3 minus lambda, and 4 minus lambda. And then copy the other entries of the matrix, -1, 1, 2, 0, 0, -5. That determinant should be 0. Now if we expand on the first column, I guess the determinant's going to be -1 minus lambda times the determinant of this 2 by 2 submatrix. So maybe that would be easier than doing lots of diagonal multiplication and adding. So that means that -1 minus lambda times -3 minus lambda times 4 minus lambda. So this product minus that product, minus -10 equals 0. So that means I can multiply both sides by -1 just to make this a lambda plus 1. And then if I do this multiplication, I've got -12 plus 3 lambda minus 4 lambda plus lambda squared plus 10. That equals 0. So lambda plus 1 times lambda squared minus lambda minus 2 equals 0. And to factor lambda squared minus lambda minus 2, I think if we do lambda minus 2 and lambda plus 1, that'll work. Lambda plus 1 and lambda minus 2. So it's lambda squared minus 2 lambda plus lambda, so minus lambda minus 2. Alright, so we have 1 is a repeated eigenvalue, and, sorry, -1 is a repeated eigenvalue. Lambda's -1 or 2. -1 is a repeated eigenvalue. So we may or may not be able to find two linearly independent eigenvectors that have eigenvalue -1. We'll see. We certainly can find an eigenvector for the eigenvalue 2. So let's look at the 2 eigenspace. So we'll solve a minus 2I v equals 0. And I erased a, but a is the matrix. Let me put it in the corner somewhere so we don't lose it. A is -1, -1, 1, 0, -3, 2, 0, -5, 4. Alright, a minus 2I is, we'll subtract 2 from the diagonal entries. -3, -5, 2, and then copy the other entries. -1, 1, 2, 0, 0, -5. So that times this unknown vector v1, v2, v3 should be equal to 0. Alright, well the third equation is exactly the same as the second equation, so I guess we can just forget about that one. And let's divide the first equation by -3 and the second equation by -5. Then we've got negative 3 over negative 3 is 1. Negative 1 over negative 3 is 1/3. And 1 over negative 3 is negative 1/3. And then negative 5 over negative 5 is 1. 2 over negative 5 is negative 2/5. So v3 is anything we want. That's a free variable. v2 equals 2/5 t. If we say v2 and put the negative 2/5 t on the other side, make a positive 2/5 t. And then, let's see, v1 plus 1/3 of v2, 2/5 t, minus 1/3 of v3, which is t, equals 0. So v1 plus 2/15 t minus 1/3 t. Let me write this in 15ths. Minus 5/15 t equals 0. So that means that v1 equals, if we put 5/15 on the other side and then subtract 2/15, it's 3/15, which is 1/5 t. So we're doing the 2 eigenspace. The 2 eigenspace equals all multiples of, well, let me say, I'll put in the t's first. So 1/5 t for v1, v2 is 2/5 t, and v3 is t. Where t is any real number. So that's all multiples of 1/5, 2/5, 1. Now if we have a one-dimensional vector space like this, we can choose any element that's not 0 as a basis. And I think if we multiply this by 5, it'll look a little nicer. Let's write 1, 2, 5. So this is 1/5 of that. Again, if we have a one-dimensional space, all possible multiples of a vector, then any other element of that space is a good basis too. And this one doesn't have any fractions. Alright, so that was the 2 eigenspace. Now let's look at the negative 1 eigenspace. So we'll solve a minus lambda I, which is a plus I, v equals 0. Alright, so now we add 1 to the diagonal and we get 0, negative 1, 1, 0, negative 2, 2, 0, negative 5, add 1 to the 4 and get 5. Well, that's nice because we basically have the same equation 3 times. This is 2 times the first equation, and that's 5 times the first equation. So we can get rid of these, and we just have 0 v1 minus v2 plus v3 equals 0. So v3 is free. Let's let that be t. Then v2 well, this is 0, so we just have negative v2 plus t equals 0. So negative vt equals negative t, which means that v2 equals t also. And then since v1 is getting multiplied by 0, that's free. That could be anything. So let's let v1 be s. So the -1 eigenspace is all vectors of the form s, t, t, where s and t are real numbers. So a natural basis is 1, 0, 0 and 0, 1, 1. All right, so now we have our three basis elements. We can see that these are linearly independent, and since that one corresponds to a different eigenvalue, that's definitely linearly independent if we add it to these. So this came from the 2 eigenspace. So anything e to the 2t times this vector, 1, 2, 5, plus anything e to the negative t, now we're using the -1 eigenspace, this vector, 1, 0, 0, plus anything e to the negative t, 0, 1, 1. That's a set of all solutions. I think that's a perfectly nice way to write it. Other people might write it in a slightly different form. Let's write this together as one vector. So this would be c1 e to the 2t plus, this is a c2, plus c2 e to the negative t in the first component, 2c1 e to the 2t. This is c3 plus c3 e to the negative t, and then 3c1 e to the 2t plus c3 e to the negative t. In case you think that looks nicer, that's just another way of writing the same set of solutions. The end.